So let's see if nuclear fusion is a plausible power source for quasars. It powers our sun after all, and all stars. Could it produce the much, much greater power we see from quasars? Well, let's look at an energy argument. What's the best amount of energy we could possibly hope to get from nuclear fusion? Well, that would be to take hydrogen atoms, lots of them, and combine them to make iron. Iron is the most stable and hydrogen is the least stable element, so this is the one reaction that gives you more energy than any other nuclear fusion or fission reaction. So what we'd need is 56 hydrogens go to one iron atom. Now, a hydrogen atom has a mass of 1.00794 atomic mass units, whereas iron has a mass of 55.845 atomic mass units, and that's something you can measure in the laboratory. Atomic mass unit, by the way, is 1.6605 by 10 to the minus 27 kilograms. So the mass of 56 hydrogen has a mass of 56 times this, which comes out as 56.44 atomic mass units, whereas iron has a mass of 55.845. So subtract them. The difference, the change in mass, is 0.6 atomic mass units, so about 1%. So when we combine 56 hydrogens to make one iron, the final result is not 56 times as heavy as the initial mass, it's actually only 99% of that. So where's this extra mass gone? Well, that's been converted into energy according to the well-known equation E equals mc squared. So the energy released is equal to the mass lost times the speed of light, c squared. So if we take 56 hydrogens to one iron, we're getting about 10 to the minus 10 joules. 56 hydrogen atoms weigh 10 to the 25 kilograms. Energy per unit mass is 10 to the minus 10 over the mass of 56 hydrogen atoms, which is 10 to the minus 25 kilograms. So we're getting a whopping 10 to the 15 joules per kilogram. So nuclear fusion generates huge amounts of energy, which is why governments spend so much time trying to build fusion bombs, H-bombs. So that seems pretty big, but how does it compare to the luminosity of a quasar? The example quasar we were looking at, 2138 minus 4427, has a luminosity of 3.4 by 10 to the 40 watts. So we can work out that's energy per unit time. We can divide it by energy per unit mass to get mass per unit time. So we need 3.4 by 10 to the 25 kilograms per second. So that's about an Earth mass every second or so to power the beast. And that's assuming that all this mass goes in is pure hydrogen and is converted entirely to iron. That actually is impossible. Real stellar reactions in the sun are nothing like as fission as this, and there basically aren't enough neutrons in the universe to go everything from hydrogen to iron. Remember, you need helium to produce neutrons. Pure hydrogen doesn't have the neutrons to do anything. So there are problems, you won't achieve that, but in the best possible situation you'd need 3.4 by 10 to the 25 kilograms per second, which is about one solar mass per day. So that's a lot of mass. So can we get this to work? Well, one way to do it, I suppose, would be to have some absolutely enormous megastar. The biggest stars in our own galaxy are about 100 times the mass of the Sun. This would need to be much bigger than that. And in the middle, some nuclear fusion is going on. But as time goes on, after one day, that will have produced a solar mass worth of iron, which is presumably is going to sit here in the middle, not doing anything. And the reaction will perhaps go on in the shell around it. And after 2 days, you've now got 2 solar masses worth of iron in the middle. And so the reaction will have to keep moving out. After 100 days, you've got 100 solar masses of iron in the middle. And so as time goes on, you're going to get a bigger and bigger and bigger core of just inert iron that can't do anything, sitting in the middle, with the fusion going on maybe around the outside. What's going to happen to that iron? It's an immense mass of iron. We remember that quasars last millions of years, so you get billions of solar masses of iron sitting in the middle. What's going to happen to it? In a normal star, you've got all your gas. Gravity's trying to pull it in towards the middle. But the pressure from the nuclear fusion reaction in the middle pushes back and stops the star from collapsing. But here in this iron core, there's no nuclear fusion in the middle. You've got the immense pressure pushing inwards and nothing much to resist it. If you do the calculations, it turns out that something called electron degeneracy pressure or neutron degeneracy pressure can hold it up as long as it's less than maybe 1 or 2 solar masses. But by the time the iron core is more than 2 solar masses, there is no force that humans know about that can stop it collapsing. So what you'd actually get is a star with an iron core that collapses inwards. And as far as we know, it would collapse down to no size at all until we have just a black hole in the middle. I can't really draw a black hole, black on black. That's the outline of my black hole. And that's going to put an end to the star. You can't really imagine nuclear fusion continuing around a black hole. The gas will just fall in. And in fact, the whole star will fall in. So it's a real problem. If we are talking about nuclear fusion with 1 solar mass per day, that's producing a lot of iron. That iron's going to form a dense core in the middle. That core will very rapidly, after only a day or two, become so massive it would have to collapse into form a black hole. And then once you've got a black hole in the middle, it's very hard to see how the star can keep going. I suppose it's possible to try another way out. Let's imagine that instead of having nuclear fusion take place in the middle of a star, let's say you have some sort of star, and you have the nuclear fusion taking place from the outskirts. I'm not quite sure how you do that. Maybe you've got heat coming from the inside, and maybe you've got more gas cascading down from the outside, and there's a shock wave where the two collide, and that's where the radiation's going on. And let's assume, this is sounding pretty implausible now, all the iron that's produced gets stripped off somehow. Maybe it's blown out in a solar wind. I'm not saying this is a sensible idea. I'm just trying to think of anything that would make this work. In this case, you're not going to have the problem with the iron core building up in the middle because you've managed to get the iron out into space. But now you're going to end up with some huge cloud of iron, presumably iron dust grains or iron molecules around there. And this turns out to be every bit as bad. If you do the calculation for this, the light from the middle here won't be able to get out anymore. It'll hit a bit of iron over here, and then bounce off it, another bit of iron over there, then bounce off it, another bit of iron over there, and it'll random walk its way out. And by the time you've got hundreds of solar masses of iron around such things, the light will take months, years, centuries to get out from this iron cloud. Which means you won't see variation on timescales less than centuries. So if the iron stays in the middle, you're in trouble. If the iron gets out, you're in trouble. looks like this nuclear fusion is just not going to work for powering quasars.